Transesterification of vegetable oils into biodiesels. The goal of a transesterification reaction is to convert one ester group into a new ester group. In this reaction, 3 molecules of methanol will be used to separate the vegetable oil into a glycerol and 3 fatty acid chains, which can serve as a biodiesel fuel and are highlighted on the right here. This reaction will be helped by a basic catalyst, sodium hydroxide, and use an excess of methanol. This reaction converts vegetable oil into a less viscous solution, which can then be used in an internal combustion chamber. The viscosity of the oil is due to the glycerol side groups of vegetable oil, which can form hydrogen bonds with each other in solution. This makes the solution more viscous and can stall an internal combustion chamber during the fuel injection process. Although this may look like a complex organic reaction, don't worry, we'll simplify it to focus on the key functional groups soon. Before we go into the reaction mechanism, let's have a brief overview of some organic chemistry terms. Organic reactions take place as nucleophiles interact with electrophiles to form and/or break chemical bonds. Electrophiles are atoms with low electron density, which would prefer to gain electrons to increase their stability. Nucleophiles are atoms with high electron density, which seek to bond with the protons of another atomic nucleus, and therefore reduce some of the electron density and make it more stable. An example of these concepts can be seen within the ester functional group seen here. The central carbon atom of the ester is bound to a more electronegative oxygen atom above it. This oxygen therefore pulls the electrons shared with carbon closer to oxygen, and leaves carbon partially positive. This leaves the oxygen partially negative as it pulls away the electron density. Sometimes breaking one bond between 2 atoms will cause one of the atoms to accept 2 electrons from the bond so that the other atom can leave. The atom that accepts the electrons must be able to stabilize the negative charge for the reaction to proceed. There are 5 different factors that help an atom stabilize the negative charge: the electronegativity of the atom, polarizability of the atom, resonance structures associated with the atom, electron withdrawing groups near the atom, also known as inductive effects, and what type of orbital the atom with the charge is in. Now, I don't want you to get too bogged down remembering all of these, so for this reaction, let's just consider electronegativity and inductive effects. The more electronegative an atom is, the better able it is to stabilize that negative charge. Remember that electronegativity is a periodic table trend which increases from left to right and bottom to top. So, just for practice, which of these atoms can better stabilize a negative charge? The methyl carbon or the hydroxide ion? If you guessed hydroxide, you're right, because the oxygen is more electronegative than carbon. Additionally, if an atom has groups near it which pull electron density away, then the atom which bears the negative charge can have some of that electron density pulled away to make it more stable. As you can see on the bottom here, the central carbon with a fluorine atom bound is better able to hold that negative charge, since the electronegative fluorine has inductive effects that withdraw electron density to stabilize the carbon, while the methyl carbon has no such inductive effects. This is the typical chemical structure of vegetable oils, which are viscous due to the glycerol side chains forming hydrogen bonds with each other in solution. Although not all vegetable oils have this 16 carbon chain seen on the left, some can involve pi bonds or ring structures. However, this carbon chain is not nucleophilic or electrophilic, so for the purposes of this reaction, the type of carbon chain is unimportant. Therefore, to simplify this mechanism reaction, we'll denote these 16 carbon atoms as R1, and we shall denote the CH2 group bound to the ester as R2. This will allow us to keep track of the number of carbon atoms in each chain and also not get too bogged down by all the carbon-carbon bonds in this structure. In the first step, methanol must be deprotonated by a basic catalyst, such as NaOH. In solution, NaOH dissociates into Na+ and OH-. The OH ion has a formal negative charge, which acts as a nucleophile. The hydrogen atom on methanol is partially positive, since it is bound to a more electronegative oxygen atom, which pulls the electron density of their shared bond towards oxygen. Because of this, the electrons on oxygen of hydroxide can grab the acidic hydrogen on methanol and deprotonate it. The electrons from the previous bond then move on to the electronegative oxygen atom of methanol. Although there are other hydrogen atoms on carbon, which the OH could have taken, they are not as easy to take as that carbon could not stabilize the negative charge as well as the electronegative oxygen atom of methanol could. The result gives the oxygen atom on methanol a formal negative charge, which can then be used as a nucleophile for the next stage. The next step of the transesterification reaction is nucleophilic attack. Here is the ester functional group on the left. This is from the vegetable oil which we want to react. As you can see, the central carbon atom of the ester group has a partial positive charge, as it is bound to two more electronegative oxygen atoms. This makes the carbon electrophilic as it wants more electron density to gain stability. Therefore, our methoxide nucleophile, which we formed in the previous step, can form a bond with the partially positive carbon. Since carbon can only maintain 4 bonds, the pi electrons shared between the carbon and oxygen move on to oxygen and give. The next step is loss of a leaving group. Now the central carbon of the vegetable oil has 3 oxygen atoms bound. All of these oxygen atoms are more electronegative than carbon and therefore pull electron density away from the central carbon. This gives it a partially positive charge. This once again makes carbon an electrophile, and the most accessible source of electrons is the oxygen atom with a formal negative charge. Therefore, an electron pair on this oxygen reforms the original pi bond with carbon. However, since carbon cannot maintain these 5 bonds, a leaving group must simultaneously leave and take its sigma bond electrons with it. This separates the ester from CH2, which we have denoted as R2. However, you might be wondering why that specific oxygen is the best leaving group, since there are 3 other atoms bound to the central carbon. Well, since the carbon which we have denoted as R1 cannot stabilize the negative charge as well as oxygen could, then one of the oxygens must be the better leaving group. Now, to better understand which oxygen is a better leaving group, let's redraw R2 as the CH2 group with glycerol attached and the rest of the vegetable oil. Now we can better determine which oxygen would rather leave. Now you probably notice that the oxygen with CH2 bound has another oxygen bound 2 carbons away, and this will allow for a small amount of inductive effects which will help to better stabilize the negative charge that this oxygen receives. However, we can also get the desired reaction with some additional help. Remember when I said that our base methanol is put into the solution in excess? This helps to ensure that there are more methoxide molecules available to act as a nucleophile, and this increases the probability of having fewer methoxide groups removed as a leaving group instead of the glycerol. You can think about this as Le Chatelier's principle as well. By adding the methoxide in excess, the concentration of one of the reactants increases and therefore drives the reaction of equilibrium forward to form more products. Now that we have separated the biodiesel from the vegetable oil by changing the ester group of vegetable oil, let's redraw what both R1 and R2 were. Remember that R1 was 16 carbons. Always write down the number of carbon atoms involved in the molecule to keep track of them when drawing new structures. The last step is for the water molecule which we made in the first step to be deprotonated by the negatively charged ion which we made in the last step. The desired final product now contains a methyl group where the original ester contained a CH2 group bound to the rest of the vegetable oil. Therefore, our final products are the ester with a hydrocarbon chain, which we will use as biodiesel, and what remains of the vegetable oil. This reaction process will then occur an additional 2 times to create 2 more esters with carbon chains, which could act as a biodiesel fuel. Now that we have gone over the small-scale steps at the functional group level, let's look at the reaction as a whole again. As you can see, each methoxide nucleophile will attack each of the carbonyl carbons. This causes the pi bonds of the carbonyl to break and be rebuilt. Then the CH2 group of the glycerol leaves, being replaced by our methoxide nucleophile. Although it is not shown here due to simplicity, the glycerol is protonated by water. However, this step is not important for our biodiesel fuel product. The arrows have been numbered on the top row to better show you their steps. Without balancing a chemical equation, you can tell that 1 mole of vegetable oil will be converted into 3 moles of our biodiesel ester. This makes for a high yield of our product. The biodiesel fuel which we have just created could be used as a better alternative to fossil fuels, as it is a renewable energy source, produces fewer emissions than fossil fuels, and is cheaper to produce. Often in organic chemistry, there is more than one synthesis pathway to obtain your desired product. Similarly, for this reaction, it could have been completed with an acid catalyst instead of a basic. However, the acid catalyzed reaction would have produced a lower yield and took longer to synthesize. If you enjoyed this lecture, consider taking Chem 281 and 282 next year, where these concepts are discussed. Now let's see how well you understand the concepts we just went over. Pause the video and try to draw out the reaction mechanism arrows required to complete this nucleophilic attack. First, the electrons on nitrogen attack the partial positive carbon bound to the more electronegative sulfur. The electrons shared between sulfur and carbon move on to sulfur. This methylates norepinephrine and creates epinephrine.